All right, second unit. I'll try to make these videos shorter. We'll first talk about rates of change. When we first talk about rates of change, we say like, what's the change between this point, 2, 3, and this point? 5, 9. And you can say, okay, 9 minus 3, okay, we changed 6 y's. But that has no context. It's like, oh, we've gone up 6. Rate of change is how quickly we've gone up over this interval. So this is why we use the slope formula, change in the y's over the change in x's, and we say, oh, we've gone up 6 units after 3 x units. That's an average of 2 y's per x. Okay, that's great. This is what we call an average rate of change, or AROC. But if I wanted to figure out what's going on right at one point, the slope of the secant, we call this, is the AROC. Well, if I understand what's going on right here, and if I look at the slope of this line or the slope of the tangent, that would be the instantaneous rate of change. And what we originally did, if we were kind of focusing on this point at 4, is we would say, well, if I knew what was going on just to the right of 4, I subtracted what was going on just to the left of 4, and then I subtract like those two values, I'd get a good approximation for what the slope was. Okay? But instead, we ended up creating some formula where we said, okay, this tangent slope, and we're going to use f prime for tangent slope. If I look at the limit as a distance approaches 0 between a function at an x value and a little bit away, and this is coming just from this is just the slope formula, this would be what this would equal. Okay, and this is like our idea that we first use a formula for an instantaneous rate of change. And what we essentially discovered was the existence of an f prime function, an existence of some kind of function where if you knew the equation of this function, this f prime, you would be able to look at values of f prime to find tangent slopes of f. We'd see, okay, I have positive values until like a 0 right here, negative values till a 0 right here, and f prime would look something like this. All right? Well, if this is some sort of x cubed, this is some sort of x squared, I could plug in values into this to get that. Now, what's important is, you will see some questions where they'll ask you, like, what is the limit as h approaches 0 of, e to the 2 plus h, maybe not e, let's go with log. Log of 3 plus h minus log of 3 over h. And you might be thinking like, what the heck are they asking me here? How do I do this? Well, this goes back to the understanding of our original formula for an instantaneous rate of change. Slope of a tangent. This is the translation, and we would take this and we would translate it to be what is the derivative at 3 of the log x function. You might not think, you might be like, where does that come from? Well, it just comes from our original formula that we found for these tangent slope generating functions. This was a slope formula for 2 points infinitely close together at a specific x value. Here you can see my function is the log function, and the point that I'm considering is 3. So like the answer to this question, we would not try to use like simplification methods. We would just like say, oh, f of x is log x, the derivative is 1 over x, and I plug in 3 and I get 1/3. That would be my answer to this question. I know that's tricky, but we may see 1 or 2 of those. You'll see it on your midterm review for sure. Okay? But what we then did is we used this formula, and this formula, instead of using it for individual functions, we used it to create rules. And the rules were like simple, power rule. If I have x to the 4th, I realize that the tangent slope generator is 1 degree less, but times a multiple. It ends up being 4 times x cubed. We learned about trig rules, where the tangent slope generator for sine is cosine. For cosine, the tangent slope generator was negative sine. tangent secant squared, and we used other rules to figure this out. Secant tangent, cotangent, negative cosecant squared, and then cosecant, negative cosecant cotangent. We learned about the product rule. If I have a product of things, it's not the derivative of the first times the derivative of the second. It's the derivative of the first, this is f prime, times the second, plus the derivative of the second, times the first. Quotient rule. Derivative of the first, or the derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. Be careful for certain functions like, oh, I forgot about the chain rule. So in chain rule, we'll do two chain rules. One is a chain of two things. Let's talk about like sine cubed of x. Two different chains. Sine cubed of x versus sine of x cubed. We talk about an outside and an inside. For the chain rule, it's just a product of the derivatives of the composed functions. So if we need to review this, I would rewrite this as sine of x cubed. The outside would be the cubed. The inside is the sine of x. Derivative of the outside would be 3 stuff squared. Derivative of the inside would be cosine. So the derivative of sine cubed x would be 3 sine x squared times cos x versus sine of x cubed. Here the outside would be the sine function. The inside would be the x cubed function. Derivative of the outside would be cosine. Derivative of the inside would be 3x squared. So f prime here would be cosine x cubed times 3x squared. Careful, just some things that trip up students. 3 over x, you don't have to use the quotient rule for that. I'd advise you to write this as 3x to the negative first, then use the product, use the chain rule, not the chain rule, use the power rule. Bring down the negative 1, I got negative 3, x to the negative second. Careful with this. Here, this is a composition of 3 functions. It's an outside, a middle, and an inside. The outside would be the square. The middle would be the cosine. The inside is the 3x. You will see compositions of 3 functions on your midterm. We'd have 2 times to the first power. We'd have negative sign, and we'd have 3. So f prime would be 2 cos 3x to the first times negative sine 3x times 3. Outside, middle, inside work from outside in. Some applications of some derivative rules, we can easily find equations of tangent lines. Whenever you're asked for an equation of a tangent line, please start with understanding this is the equation of a line. Make sure you understand that you have numbers. This is going to be a function value. This is going to be an x value, and this is going to be a tangent slope value. We would need to find some things. F of 2, that's going to be 8, 10, 7. I got y minus 7. I got x minus 2. And then we would just need f prime of 2. We'll find the tangent slope generating function, 4x plus 1, plug in 2, I get 9. And it's the equation of the tangent line. Find locations where lines are tangent to this and parallel to this. Well, if you have a tangent slope generator, you can see when it generates specific tangent slopes. Here, the slope of this line is 9. Equations are what we're going to use to help find specific tangent slopes. When does 3x squared minus 6x give us 9? Now, don't try to factor this and set it equal 9. That's not going to help you. Instead, move everything to one side because it's a quadratic. Maybe factor out a 3. Then factor. We'll get 3 and negative 1. Okay? Horizontal tangents, we'll find horizontal tangents very, very frequently. Horizontal tangents are when our tangent slopes are 0. When does my tangent slope generator generate a slope of 0? Here I get 4. We can have piecewise functions. You can be asked to ensure the differentiability. Differentiability means you are not only continuous, but you have no sharp points. So, to ensure differentiability, we need to check 2 things. Are we continuous? Does the first little piece meet up with the second little piece? Well, I get at 2, that's the most important part. 8a equals 4 plus b, okay? This must be an equation that must be true if we are to be continuous. But the problem is I don't know what a and b are. This is where the second point comes from. No, second equation comes from. Having no sharp points. No sharp points mean the tangent slopes must be approaching the same values as well so that they don't meet up at a sharp point. You can't meet up like this. Instead, you have to meet up so it's nice and smooth, like that. So, the derivative of the first piece is 3ax squared, but I'm plugging in 2, and I get 12a. The derivative of the second piece is 2x, but I'm plugging in 2, I get 4. That gives me a is 1/3. Once I get a is 1/3, I can find b by plugging in 1/3 in for a. That's 12/3. That's -4/3. Okay. Other problems with table problems are derivative rules problems, where we don't have just x's. I have x's in like g of x. Just don't forget that your rules still apply. If you see x squared over g of x, don't say the derivative is 2x over g prime. It's a quotient. Use the quotient rule. Derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. I would then plug in 8. Now let's look at g of 8. G of 8 is 2. Okay, so I got 16 times 2 minus g prime of 8. G prime means the slope of the tangent. The slope of the tangent is the slope of this line segment. You would use rise over run to say, okay, I'm going down 1 over 2. That's -1/2. Times 4. This is 2 squared. That's 4. So I have 32 plus 2 is 34 divided by 4. 17 over 2, something like that. If I have something g of x cubed, this is a very tricky one. A lot of students think that the derivative of g of x cubed would be just 3g of x squared. That'd be wrong. G of x has an outside and an inside. The outside is the cube. The inside is the g of x. Derivative of the outside would be 3 stuff squared. The derivative of the inside would be g prime of x. So we need to multiply by g prime of x. Derivative of 2x is 2. Excuse me. If I plugged in 1, let's look at 1. G of 1 is 2, 3, 4. G prime of 1 is also -1/2. So this is 4 squared times 3. I'm not going to worry about doing the value. Times 1/2 minus 2. Same goes for f of g of x. Outside is the f of, the inside is the g of x. The derivative of f of g of x, it's not a product. You don't use the product rule. You use the chain rule. So this is f prime of g of x times g prime of x. This is like the definition of the chain rule. Now, if I were to ask what this is at 1, you would make sure that you worked inside out. So you would do g of 1. G of 1 is 2, 3, 4. And then I would go f prime of 4. F prime of 4 is the slope of this line, which is -1. G prime of 1 is -1/2. This would be +1/2. Okay, so that's table problems. Let's also not forget higher order derivatives. This notation for derivatives, dy dx is just like y prime. D cubed y over dx cubed would be like y triple prime. So if I have y prime and I go to y triple prime, I need to take the derivative of this twice. So the first derivative of dy dx would be d squared y over dx squared. That'd be 3x squared. Derivative side is cosine, but don't forget the derivative of the inside. That's times the 2. And then one more derivative would give me the third derivative, 6x. This would be positive sign. I'd multiply by another 2, and I get 4. All right? So that's a quick overview of derivative rules.